Okay, so we're going to start with this regular hexagon whose vertices are labeled P1, P2, P3, P4, P5, P6. And I'm going to define three dashed red diagonals. The first one connecting P1 to P3, the second one connecting P1 to P4, and the third one connecting P2 to P6. Now, because I have these four collinear points here along the third diagonal, let's go ahead and label them as A, B, C, and D. Okay, now I can of course compute the cross ratio over A, B, C, and D over here. What is the cross ratio? A, B, C, D. That is the product of the distance AC times the distance BD divided by the distance AD divided again by the distance BC. So we have a product of two distances in the numerator and divided by a product of two distances in the denominator. Okay, now what I'm showing here up above is this cross ratio. This particular cross ratio here for the regular hexagon is 2. Okay, now let's go ahead and define this construction cyclically. Okay, I'm going to now make P2 play the role cyclically of P1. What do I mean by that? I'm going to go ahead and add 1 to all the indices that define each diagonal. So for example, this first diagonal here is defined by indices 1, 3. Let's add 1 here. So I'm going to get P2, and this is going to become P4. Okay, so I'm going to add 1 to each one of the extremities. I'm going to add 1 to the indices that define the endpoints of this diagonal, and I'm going to add 1 to the indices that define the endpoints of this third diagonal. So let's look at that. So I'm going to go over here now. So I have first diagonal going from P2 to P4, a second one from P2 to P5, and a cross diagonal going from P3 to P1. And again, I have the same cross ratio, A, B, C, D. So distance AC times distance BD divided by the product of distances AD times BC. Okay, and I'm reporting it here, it's 2. Okay, and again I can cyclically move on to the third vertex and report that, and the fourth vertex, etc., all the way to the sixth vertex, and just repeat this construction cyclically and measure 6 cross ratios. Okay, now what you're seeing here is that because this is a regular hexagon and there's going to be sort of six-fold symmetry, all these constructions turn out to produce the exact same cross ratio equal to 2. Okay, and this can be easily shown. Okay, so I'm reporting here the 6 cyclical cross ratios. I'm also reporting here the CR6, so you know the specific cross ratio I'm drawing, and the sum of these 6 numbers, so 6 times 2 is 12, and their product, right? So 2 to the power of 6 is 64. So here is the sum and the product. Okay, now I can freely move the position of the 6 defining points of this hexagon. So let's go ahead and drag, for example, P2 around, and let's see what happens to these 6 cross ratios and their sum and their product. So I'm going to move around P2. So as I move P2 around, first really interesting thing happens. Everything is variable, okay, except for the 1, 2, 3, 4th cross ratio. So the cross ratio with respect to the 4th vertex, this one here, as I move P2, is not being affected. Notice how it's actually latched to 2 there. Okay? It's latched to 2. Why is that? That's because when I move P2, and only P2 in this construction, my 3 diagonals are unaffected. Okay, so I can move P2 around, and they're going to be unaffected. Now, the moment I touch any one of the remaining 5 vertices here, you're going to see that this 2 here is going to get disrupted. So for example, let's move P6 a bit. So I'm moving P6. Now I'm no longer with a 2 over there. Okay. Now notice that as I move P6, there's one of the cross ratios that is unaffected. That's cross ratio with respect to the second vertex. It's here at 3.32. Let's look at it. If I go to the second vertex, there it is. Cross ratio with respect to the second vertex. Doesn't matter that I'm no longer in a regular hexagon configuration, but motions of P6 do not affect the the 3 diagonals defined with respect to P2. So I get 3.32 constant. Okay, now what this video is about is actually a different phenomenon. Let's go ahead now and go back to our regular hexagon. Here's our regular hexagon. And I want to define a different ordering to compute this cross ratio with. Okay, so now I'm computing the cross ratio in the, the usual way, and it's actually represented as AB semicolon missing here CD. So we get the sort of AC BD divided by AD times BC. But let's choose a different ordering of these letters, and I'm going to choose. I have six orderings here that produce 6 distinct cross ratios. I'm going to choose the third ordering, and the third ordering is ACBD. Okay, and what does that mean? What cross ratio am I talking about here? I'm talking about a cross ratio where I'm going to measure the distance between AB. I'm going to multiply that by the distance between CD, and in the denominator I'm going to have AD times CB. So the cross ratio works that way, right? So you take the first letter, the distance from the first to the third entry, that gives you a first distance. So in this case here, the first and third are A and B. Then you multiply that by the second and fourth, CD. Then you divide that by a product, which is made up of the first and fourth, so in this case AD, and the two middle ones, so CB. Now it turns out that with respect to the very first measurement, okay, this very first one, ABCD, if you actually do the third choice here, ACBD, 1 minus gamma, you're going to get the 1 minus the first cross ratio. So recall the first cross ratio was identically to, let me put it back there, okay, if I change this, if I permute these letters, and now I have ACBD, what I'm going to be getting here is 1 minus that. So I had 2 there, right? So what I'm going to be getting here is 1 minus 2 up to a signal, so it's actually being reported here as 1, but this should have been minus 1. Okay, so I'm ignoring signals. All my cross ratios are positive right now. Okay, so you can think of this as being lambda minus 1. All right, so let's check the results. If I do this, I get 6 cross ratios that are equal to 1. Cyclically, the second cross ratio here, which is this one over here, is shown here as being 1. Of course, I can cycle this to the third vertex. I get 1 again, to the fourth one. So I don't need to do this because I'm already reporting all 6 up here. The sum of these 6 is equal to 6 times 1, which is 6. And the product of the 6 times 1 is 1 times 1 times 1 times 1 times 1 times 1. I mean to say 1 raised to the power of 6 is also 1. Okay, now the result of this video is the following. Now let's go ahead and move one of the vertices around. Let's move P2 around. Look at what happens. When P2 moves around, every single cross ratio is varying except for the fourth one, which is stuck at 1 as before. Why is it stuck at 1? Because as I move P2, I'm not affecting the construction with respect to P4. These 3 diagonals are frozen. But something else very neat is happening. The sum of cross ratios is variable. However, the product of cross ratios is stuck at 1. Okay? Let's go ahead and move another vertex around. Let's move this vertex around. Now you can see that as before, the second cross ratio over here is at 7.57, because if I look at the construction with respect to the second vertex, when I move P6, I'm not affecting that construction. So that means that this number here is going to stay constant. But what's magical about this is that the product, regardless, stays at 1. Okay? So the main result here is that I can move all of my vertices away from that regular and convex situation and just construct any old hexagon, convex or concave, where though the 6 cross ratios are going to be distinct numbers, their product is going to be stuck at 1. Okay, so if you cycle through the 6 constructions, or the 6 triples of diagonals, the way defined before, if you just cycle through those, okay, you're going to get 6 sets of 4 collinear points. Each one of them is going to have an associated ACBD, so they're being reported here, the 6 cross ratios. They're distinct numbers in general, okay? However, the product of cross ratios is somehow magically invariant and equals to 1, even when my polygon is auto or self-intersected, like so. Okay, so you can freely self-intersect the polygon, and you're going to continue to measure the product of cross ratios equals to 1. Okay, so you can see here that in this case, the C vertex is actually going outside of the sort of the central area of the polygon, but we're always going to get 3 intersections between these 3 non-parallel diagonals. We're always going to get 2 intersections, sorry, and we're always going to be able to build a quadruple of collinear points over which we can compute the specified cross ratio ACBD. Okay, so it doesn't matter if this polygon is horribly self-intersected or it's back to a simple polygon like so. Okay, we can take it back to a simple polygon as we had in the beginning. The product of cross ratios is invariant and equal to 1. Okay, let's bring that guy back in. Where is it? I don't know. It's gone off to infinity. There it is. So here's a B, C, D. I think I can put B outside as well. Let's see if I can do that. Perhaps if I move this guy around. There we go. So now we have the extremities of this lone diagonal here, A and D, are over here, and the intersections of P2, P6 with this diagonal is happening here at B. Okay, if I move this point around, you're going to see that this intersection is changing, but it's going to be collinear because it's an intersection with this line. And the intersection of P3, P6 with this horizontal line, or with this third line here, is C. All right.